Sorry, you should. Oh, you should. Okay. Good afternoon. Our speaker today is Gayathri Gururajan. She just got her PhD from the Astrophysics Laboratory in Marseille 1 week ago, working with Matteo Betermin and Patrice Toilet. And now she moved for a postdoc here in Bologna, working with Talia, Pozzi, and Cucciati. She's an expert on studying dusty galaxies and gas reservoir in galaxies. And today she will tell us about probing the gas reservoir of Z dusty galaxies. Please, the room is yours.
Hi, everyone. Thank you for being here in person and for all those who've connected through Zoom. And today I'll be talking about the work that I did for my PhD thesis the last 3 years, which mainly is on understanding the properties of gas reservoir of high redshift dusty galaxies using ALMA observations of atomic particles. Okay, looks like I can't. Oh yeah, okay, thank you. So before we begin, the main reason it's important to understand the gas reservoir, it's connected to the star formation. Let's say in this plot, we see the star formation rate density as an evolution of redshift. And what we can see here is roughly at a redshift of about 1 to 3, there seems to be a peak in the star formation rate density. Now, this plot is basically showing the volume average star formation rate density. And some of these galaxies, which are supermassive and very dust rich, have a higher contribution to the SFRD, especially in these redshift range. But what happens when we see the molecular gas density as a function of redshift? We see a very similar trend as the SFRD, showing that on a global scale, molecular gas seems to be the main driver of star formation. But what really happens in the scale of individual galaxies, especially the ones that are most intensely star forming? For this reason, we study some of the most massive galaxies with very high star formation rates. In the plot here on the right, what we see is the star formation rate density as a function of molecular gas density. Now here, if we notice on the black solid line, what we see is galaxies can form more stars by having simply a higher gas mass. But sometimes you can have a boost in the efficiency of star formation for certain galaxies, by which for the same amount of molecular gas, they could have a higher star formation rate. So what really is suspected in some of these most intensely star-forming galaxies is that there is a combination of both a large gas reservoir as well as some sort of mechanism that's playing in order to increase or improve the efficiency of star formation. Now, these galaxies are particularly interesting because they are thought to be the progenitors of some of the most massive galaxies in the clusters that are seen today. So, as what we again see in this plot is that the gas fraction, when plotted as a function of redshift, there seems to be a higher molecular gas, especially in these redshift range where there is a higher star formation rate density. Since we can't really observe directly the H2 content in these galaxies specifically, what we do is use certain tracers in order to characterize the gas reservoir. And by characterizing the gas reservoir, what we can try and understand is what is the major mechanism that drives the star formation and what exactly is the nature of these dusty galaxies. So in this work, we mainly rely on 3 such gas tracers. The first one is the carbon monoxide molecule. It's one of the most commonly used tracer for the molecular hydrogen to estimate the molecular hydrogen content in a galaxy. And it has many rotation transitions, and specifically the 1 to 0 transition is used in order to estimate the molecular gas content. But in this case, we need to assume a CO to H2 conversion factor, which is known as the alpha CO. But this alpha CO comes with its own limitations. For instance, it varies with density, metallicity, and is also affected by physical processes like mergers. Additionally, in the case of some of these high redshift galaxies, this 1 to 0 observation may need not be feasible all the time. So we sort of observe higher rotation transitions. And in order to estimate the molecular gas mass using them, we'll need to assume an excitation factor in addition. The second possibility is to use the neutral carbon emission fine structure lines in order to trace the molecular gas mass. In this case, both the transitions of C1 trace extended gas and remain excited over a large range of temperature and densities. But even in this case, as you see in this very complicated formula, we still need to understand a few factors. For instance, the Q1 to 0 or the C1 excitation factor needs to be constrained. But this is possible if we have both the C1 transition observed, because we can estimate what the excitation factor could be. Additionally, we do need to assume a C1 abundance, which is also known to vary with metallicity and density. And our third option is using a dust mass of the galaxy as an estimator or as a tracer of this molecular gas. In this case, we also need to assume a gas to dust ratio, which, as we see in the plot on the right, varies again with metallicity. So we have 3 tracers, and all 3 of them have their own limitations. So how do we really study the physical properties of these galaxies? And how efficient is C1 specifically in comparison to the other 2 tracers? And since all of them have their own limitations, is there a way we can cross-calibrate these tracers and check whether they agree with one another or not? So for doing so, we specifically study the sub-millimetric galaxies. In this case, the sub-millimetric galaxies, or the SMGs, they're really bright in these wavelengths, whereas they're almost invisible in the UV optical wavelengths. They represent a very complex population in terms of morphologies, and they always have very high star formation rates. Although these galaxies are really bright, it does become challenging, 1, to detect fainter lines, and 2, to make large samples or for observing a line, and 3, also to observe at higher resolution. For this, we can exploit the strong lensing effect in these galaxies. As one, we can try and use the magnification factor due to the lensing configuration in order to amplify the fluxes for the lower resolutions, for the fainter sources. And 2, we can also use the effect of lensing, which sort of stretches the sources. Thereby, we can resolve the source in multiple beams, and we can study a much higher resolution, let's say even up to sub-kiloparsec scales. And in this work, we use both these facets of strong lensing in order to first build a large sample, and second, to go into higher resolution. Specifically, we use the SPT-SMG sample. And basically, in the 2500 kilodegree survey of the SPT telescope, they identified many candidates, many lensed SMG candidates. And when followed up with spectral scans using ALMA over a decade, what we identified is almost 81 galaxies, which have their spectroscopically confirmed redshift, and most of them were gravitationally lensed. Now, what are the insights we can gain using lensed galaxies, especially moving to higher resolution observation? And can this help us to understand the morphologies of these DSMGs? So today, first, I'll talk about a larger sample of C1 selected galaxies in order to test out the properties of C1, and then about the higher resolution sample, and lastly, I'll conclude. So in order to study the properties of C1, especially in these SMGs, what we do is to select a sample of roughly 29 galaxies in which both the C1 transitions are in the observable windows of ALMA. Now, since it's the SPT-SMG galaxies, we have a rich ancillary data of mid-J and low-J CO lines, and all of them have been modeled, all of them have SCT modeling, due to which we can have an estimate of the dust mass. And from our observations, we target the C1-120 and C1-221 transitions of all these galaxies, along with the CO7-6 and CO4-3 for some of them. Now, if we compare the properties of C1, which is an extended gas tracer, to IR, which is more an SFR tracer, we can sort of get this integrated Koenig-Schmidt relation. In the top panel, we compare the C1 1-0 transition along against this IR luminosity for our sample, along with a sample of SMGs, main sequence galaxies, and local galaxies. What we see is the relation is sort of linear for both the samples, for the main sequence and local galaxies, as well as for our SMGs. But in the gray line, what we see is if we try and combine the relation for all the galaxies, we sort of flatten the relation. This could be due to the fact that the two different samples have two different trends and we're sort of combining them. But this is in short. But we don't see this sort of effect for the C1 2-1 versus the IR, but this could possibly be due to the higher excitation of C1 2-1. Here's the plot by Valentino 2020, where they compare the C1 1-0 versus CO 4-3 against the C1 1-0 versus LIR, and in that case, the C1 2-1 versus CO 7-6. So basically, C1 1-0 versus CO 4-3 is an extended versus a slightly denser gas tracer, which could be a proxy to the density. And the C1 1-0 to LIR could be a proxy to the star formation rate efficiency. When they overlay the PDR contours by Kaufman 99, what they find is these ratios sort of are parallel to the density and the radiation field of ISM modeled by these PDR modeling. And here they plot their sample of local galaxies, SMGs, and main sequence. When we plot our SPT-SMGs on this plot, what we see is we have a very similar radiation field intensity as well as density when compared to the SMGs of their sample. But we do have a slightly higher radiation field intensity and density compared to the main sequence and the local galaxies, despite there being an overlap. Furthermore, since we have two C1 transitions in our observations, what we can estimate is the C1 excitation temperature. And this temperature here on the y-axis is compared with the dust temperatures from our SED model. What we find is mostly we have galaxies which have higher dust temperatures than the C1 excitation temperature. This could be due to the fact that dust being in the center could be more heated by intense star formation activity, whereas the C1 being a more extended gas could be in a more extended region. Also from this plot, we don't really find candidates which have extremely high excitation temperature like the GN20 in comparison to the dust temperature, which don't advocate very strongly towards optically thick dust models. But the main goal of this work was to try and estimate, try and compare the three traces with each other and see if we can cross-calibrate them. So basically, in this scenario, we have three unknowns in all these three traces, and we try to find a relation between these unknowns in terms of all the other quantifiable quantities. For instance, let's say in this case, we can get a relation for the C1 abundance and the alpha CO as a function of all the other parameters from our observations. And when we check this relation in comparison to the LIR, for our sample as well as the ancillary data that's available, we can see how there's not a very large scatter in this relation, as well as we don't see a significant trend with the IR. The same holds true when we compare the gas to dust ratio and the alpha CO, as well as the gas to dust ratio with the C1 abundance. So basically, we don't really see a strong scatter in all these three relations, and whatever the scatter we see can be reproduced by measurement uncertainties, which means the traces do agree reasonably well. For all these three traces, we don't see a strong trend with LIR, but however, let's say all the traces have the same sort of trend or something, it could be compensated because we're still using a product of them. And let's see what the tracer values are with two different scenarios of alpha CO. Assuming a higher alpha CO, which is more like Milky Way values, what we find is a low C1 abundance and a higher value for gas to dust ratio. On the other hand, if we assume a Euler-like alpha CO value, we find very high C1 abundance and very low gas to dust ratios, which could be possible for extremely metal-rich environments. So we don't really have a way to disintegrate which population our sample is representative of. For instance, the y-axis here shows the depletion timescales calculated with the CO gas mass using both the alpha CO regimes. For the diamonds are for the 3.4 alpha CO and the squares are for the 0.8. Either our sample could be more a main sequence-like population, or it could be a more starburst-like population. So a way to identify which one it is to try and understand a way to actually find the absolute value of these traces. Can higher resolution observations provide us some clues on some more clues on the nature of these galaxies? For this, we select a sample of 3 such galaxies and we observe them at a resolution of 4.3 arcseconds for the C1221, CO726, and the dust continuum. In all the 3 plots, we see the integrated spectra of the galaxies as a function of their frequency and velocity. And we can see that all the spectra are quite asymmetric, and yeah. And here's the continuum morphologies of these galaxies. So O103-45 shows a very nice ring-shaped morphology with a bright part in the northwestern part of the ring. And in the case of 2147-50, we see these extended arcs and counter image from the compact brightness that we see in the northeastern part of the ring. On the other hand, 2357-51 is quite compact. So firstly, we try to understand in their image plane, how exactly is their velocity distribution. Now, if we construct a peak velocity map in the pixel-wise emission of these galaxies, for instance, for 2147-51, we see that the velocity map for C1221 and CO726 is very similar, which ensures the robustness of the method. And secondly, we can see the smooth gradient, which sort of suggests that these galaxies could be rotating structures. A similar test when performed for O103-45 also showed a nice smooth gradient, which could say that these 2 galaxies could be rotating structures. But to understand further, we would need to look into the source plane of these galaxies. In the case of 2357-51, if we go back to the integrated spectra, we see this sort of double beak-like structure. So when we construct the position velocity diagram of this galaxy along the right ascension axis, what we see is this sort of 2 blobs, which are connected by this bridge-like structure. Could this be a hint towards a merging scenario in these galaxies? We still need to find out. So for that, what we first do in the image plane itself is to build a Gaussian decomposition for every the spectra extracted in every line of sight, and one component to fit the lower velocities and one to fit the higher velocities. And the velocity map constructed with this decomposition method shows us a blue component and a red component, where the gradient for both the lines of the blue component seems to be very smooth. On the other hand, for the red component seems to be a bit more distorted. And when we overlay the contours of the continuum emission on these components, we can see they align better with the red component than the blue component, which could hint towards some sort of intrinsic differences between these components. But all this was done on the image plane. What does the source plane of these galaxies tell us? For this, we need to model the lensing configuration of these galaxies, and we use the visibility-based modeling code known as VisiLens. So here on the 3 panels, we show the continuum lens model for all the 3 galaxies. And in order to model the continuum emission, what we choose is our lens parameters and our source parameters. We set a source profile and then try and model based on the available data points. And in order to model the line emission configuration, since we have a sufficient signal to noise ratio, what we do is to divide the entire line emission into bins and model each of them. So with this, what we can get is this source plane position source plane velocity maps for these galaxies, where each of these square basically represents the intrinsic position in every given velocity bin. So in the case of 0103 minus 45 and 2147 minus 50 in the top panels, we can see some sort of a smooth gradient, which could further help us to conclude that these sources could be possibly rotating disks. On the other hand, in the case of 2357 minus 51, it's a bit more complicated. So we're still not sure if this could be considered as a rotating disk, but it's slightly hinting towards a merging system again. Another important thing, what we can do with these galaxies is to try and understand what is the contribution of differential magnification. For instance, in our the larger sample, what we did was we simply assumed that there was the line ratios in our ISM plots. Basically, when we compute line ratios, the magnification effects do cancel out. But we want to see whether that's true or not by actually quantifying the effect of differential magnification. In this case, the three plots here basically are the magnification at every velocity bin compared against the observed spectra of the galaxy. And what we see, at least in these two panels, is that the line profile seems to be distorted, or the asymmetry in this line profile seems to be arising from magnification effect. Whereas for this galaxy, it could still be something more intrinsic. But in the case of line fluxes, when we compute the effect of magnification, what we see is there's not a very significant effect of differential magnification on the line fluxes itself. Therefore, this sort of justifies our assumption previously when we used line ratios to mitigate the magnification effects. So we continue to do the ratio analysis in our image plane itself. Now, firstly, this is very similar to the plot that I showed earlier, and this is the Valentino 2020 comparison sample. So when we place our three high resolution galaxies, what we see is the global properties are quite similar to the SMGs. That is, they have a very similar density and radiation field. But since we have high resolution observation, what we can do is to study the variation of the radiation field and density across the ISM of these sources. What that shows us is that the ISM is really quite heterogeneous. So although these global properties do seem to be very similar to the SMGs, there is a large variation in the radiation field and density in their ISMs, which is true for all our three sources. And lastly, from our lens modeling parameters, we can sort of approximate the dynamical mass of these galaxies with a simple Keplerian approach. And when we compare the dynamical mass with the two different alpha CO regimes, which we were not able to disentangle earlier, what we can say, at least for these galaxies, is that the alpha CO of 0.8 was more agreeable with the dynamical mass estimate. But when we use a higher alpha CO for these galaxies specifically, there was a tension between the dynamical mass and the gas mass estimated. Therefore, these galaxies do represent a very short depletion time scale disk-like structures, and the other one could be a merging system. So to conclude on the nature of these intensely star-forming high ZD SFGs, firstly, with their gas content, when we compare the three traces, they do agree well with each other, and there's no strong global trend with LIR, although there could be a trend intrinsically, which we miss in our analysis. When we study the ISM properties, on the first look, they are very similar radiation field intensity and density to the SMGs. But moving to high resolution observations, what we can see is there is a large heterogeneity in their ISM. And the excitation temperatures of these galaxies are quite similar to the other SMGs in literature. And they have a lower excitation temperature than the dust temperature. Moving to higher resolution analysis, in a sample of just 3 galaxies, we were able to find a morphokinematical diversity from rotating starbursting disks to merging systems. So if we push such an analysis to a larger sample, we could potentially understand the dominant morphologies in these redshifts. And in this sample, we did not find strong effects of differential magnification on the line fluxes, but the line profile seemed to be affected by magnification. Thank you.
Questions for our speaker?
So I already missed the point. What's the mass that you derive from the systems?
It's about 10 to the
10 to the 11. The dynamical mass.
no, the gas mass. Yeah, the dynamical mass is around 10 to the 11.
The dynamical
Yeah.
mass. Okay. So it's our goes down. The stellar mass will be quite much
Low,
lower.
yeah, hopefully.
The
But
10 and the 9. Kind of say,
I'm not sure,
the kind of
but
system.
we will be definitely able to answer this question in the very near future with JWS. We're starting to do follow-ups where we can try and estimate the stellar mass of these. But they do have a high gas fraction. Because we tested out the dynamical mass, especially with 3 different gas fractions, 0.5, 0.8, and almost 1. And in all cases, they did have a very high gas mass.
Okay.
I have a question about the velocities. In your velocity maps, it looks like the zero is not always symmetric. In one of the cases, there was also 700 kilometers per second. So the question is, how do you choose the zero of your velocities?
So what we firstly, we have the spectroscopic redshifts from previous surveys as well. So we compute the zero of the velocity using the CO76 spectroscopic redshift. And here for this system especially, we can see the higher velocity because the tail of this emission seems to be moving to very high velocity.
And a related question, do you also have measures of the velocity dispersions of the gas and how
So this is
typical values?
no, this is something we really wanted to do, but we couldn't because with this resolution, it was hard to construct the full pixelated lens reconstruction. And without that, when we tried on the first time, we were really not able to see the dispersion. Maybe we were missing it out because of the limitations. So we're starting to work on that and hopefully.
I have a very naive question. So in the local universe, normally you have most of the regular gas and cold phase. So in the 2 to 1 and 1 to 0 to lines. So in this case, this is not true by redshifts, or can you constrain in some cases the line spectra?
Yeah, there has been a few papers where they were doing the SLEs for these lines on these galaxies. But here we're still using a lower JCO in order to trace the molecule. The CO76 here, we don't use that to probe the molecule. It's still the CO10 maximum of the 3. And the distributions, I'm not sure whether I've compared it with, I haven't, so I don't know if those studies did or not. I have to check and get back to you.
I have one. So to wrap up, at the end, if I understand correctly, you said that most of your galaxies should have a bar star formation because the alpha 08 is more compatible than the other alpha.
Yeah, the depletion timescale at least for these galaxies, but we are really limited by sample size here.
Okay.
Because when we do the dynamical mass comparison with the alphas, we're using only 2 galaxies in order to say that. But another way of actually getting that is by increasing the sample size or using other ways.
Okay, so maybe you cannot answer with yet. My question was, should I interpret that as a selection bias of the small sample you're using, or that really a high fraction of the galaxies at that redshift are characterized by a short depletion time? So is it really the population or is it selection bias? Or you cannot answer it?
I cannot answer this yet, but there definitely could be a bias, but not sure. Maybe we need other factors like metallicity in order to actually understand.
Okay. Any questions from the remote audience? Doesn't seem so. Or from the room? Okay, then we can try and speak.
Vedi? Very nice, very nice, very nice.